In this video, we talk about set associative guess. So basically, the set associative guess combine the idea of direct map guess and the fully associative guess. Of an n-way set associative guess mapping is like the direct map guess in that a memory reference to map a particular location of guess. However, the thing different from the direct map guess is that a memory reference map to a set of several guess blocks. Similar to the way in which the fully associative guess work, instead of mapping everywhere in the entire guess, a memory reference can map only to the subset of guess slot. So here the graphical representation of the set associative guess. Let's assume we have a number of guess blocks per set in set associative guess, and that's vary according to the overall system design. In this example, we have the two-way set associative guess and have a two-way to represent it. One is the conceptual line, and the other one we call that the logical view, and also the other one we call it the linear view. So basically the logical view, here the guess gonna be represented by two-dimensional metric. We have the two-way set associative guesses, mean take up the set right here contain a two block. So in here we have the set 0 contain block 1 and block 0 and block 1. Set 1 contain a block 2 and block 3. Set 2 contain block 4 and block 5. Okay. Two ways mean that a two block in a set. Again, this is a logical view, so that's a two dimension, that's called metric representation. However, in reality, the guess memory gonna be represented by a linear view. So in this way, you can see that the same concept, but the now the block gonna be represented by a one column. So set 0 again contain the block 0 and block 1. Set 1 contain block 2 and block 3, and set 2 contain block 4 and block 5, and so on. So again, this is a two-way set associative guess. So each of the set contain two blocks. Okay. In set associative guess mapping, a memory reference is divided into three fields. That's the tag, the set, and the offset. Okay. The same with the way in direct map guess, the offset field choose the word within a guess block, and the tag field uniquely identify the memory address. The set field, on the other hand, determine the set to which the memory block map to. Okay, so here's an example to show how different fields gonna be used to mapping the address in the memory to the cache. Suppose we are using two-way set associative mapping with a word addressable main memory of 2 power 14 words and a cache with a 16 blocks. Okay, and where each block contains 8 words. All right. So in this way you can see that because the cache have the total of 16 blocks and we have a two-way set, so it means each set have the 2 blocks. So total we have the 16 divided by 2, we have the 8 set in the cache. Okay. When we have the 8 set in the cache, so the number of bits in order to represent each of the set gonna be 2 power 3 equal to 8, right? So that the set field equal to 3 bits because 2 power 3 equal to 8 set right here. Also, we can see that the offset field equal to 3 bits because we have each block contain 8 words. So 2 power 3 equal to 8. So the offset field gonna be equal to 3 bits. So that's used to identify each of the words within one set, one block. Okay, sorry, it's within one block, and the tag field gonna be a 14 subtract 3 equal to 8 bit. Okay, so here you can see that the tag gonna be 8 bit, the set gonna be 3 bit, and the offset gonna be 3 bit. Total we have the 14 bit. That's the number of words in the main memory. Okay. So that how the set associative associative cache we address between the main memory and the cache. So we can see that with fully associative and a set associative cache, a replacement policy is invoked when it becomes necessary to evict a block from the cache. So in this case, the cache is full, and then new data need to be written into the cache. So one of the existing block need to be evicted. So you need to some kind of a replacement policy in order to do that. An optimal replacement policy would be able to look into the future to see which block would be needed for the longest periods. Although this is impossible to implement an optimal replacement algorithm because we don't know what's gonna be which block gonna be needed for the future operation. But it's instructive to use this as a benchmark for assessing the efficiency of any other scheme we come up with. Right, so the optimal replacement policy is the upper bound of the performance, and if we can devise any practical one close to just optimal replacement, so that's going to be a good scheme for the replacement.